Modern science has developed a strong understanding of the steps needed to transform inorganic molecules into living organisms, a process that involves progressively complex structures, a precise arrangement of atoms at just the right time, and a seemingly limitless source of energy. Yet, despite these advances, and even with significant strides made in simulating the process artificially, our brightest minds just continue to grapple with the question of how life on Earth actually started. This isn't to say there aren't plausible theories. In fact, 3 of them are widely supported. The real challenge is that for the scientific community to reach a consensus, we must first reconstruct what Earth looked like billions of years ago. Achieving this requires careful examination of remnants from hundreds of millions of years of planetary chaos, considering that life did not emerge along a neat linear path, but rather through cycles of unimaginable destruction and innumerable rolls of planet-sized dice. Now, we'll get into all of it in this video, and if you didn't believe in cosmic serendipity before, well, the reality of how the earliest terrestrial organisms on Earth came to be might just convert you, so let's get into it. The groundbreaking Miller-Urey experiment. The Miller-Urey experiment stands as one of the most groundbreaking scientific breakthroughs in all of history. Conducted at the University of Chicago in 1952 by Professor Harold Urey and his student Stanley Miller, the experiment aimed to simulate the conditions believed to be present on prebiotic Earth and to kickstart the earliest steps toward organic life. Key to the experiment was the use of only the most basic inorganic constituents, along with a dose of artificial electricity. If the experiment bore fruit, it would once and for all confirm that life can arise from a completely lifeless environment, or at the very least prove that the initial steps were possible, even if many more rungs on the ladder were required before reaching rudimentary microorganisms. To be more precise, the ingredients provided are all naturally occurring and would have theoretically been present on Earth billions of years ago. These would be methane, ammonia, hydrogen, and water. Note that the basic atoms in these compounds are also those required for life, which we will explore in a bit more detail shortly. For now, just be aware that the experiment essentially involved coaxing atoms into forms that are more conducive to life. It also is important to note that the experiment aligns with the primordial soup theory, which postulates that life on Earth arose when the necessary ingredients occurring naturally on the surface were stimulated by energy, ultimately leading to life as we know it. As for the origins of those ingredients, the matter is somewhat complicated, and we will also get to that in due course, so stick with me today. Alright, so I think we should acknowledge that this experiment does sound a bit like Frankenstein's monster, with life springing forth from bolts of lightning, and also recognize that, like Dr. Frankenstein, Miller and Urey were successful. The duo made a landmark scientific discovery when they managed to create amino acids out of nothing but a mixture of gases and water. Now, yes, amino acids are no Frankenstein's monster, but they are the building blocks of proteins, which in turn are fundamental for life. The results, simply put, were revolutionary, definitively ending the long-held belief that life arose through what was known as spontaneous generation. Promoted by the Greek philosopher Aristotle, this theory maintained that life on Earth emerged from its corresponding material. For example, slime gave birth to oysters, decaying flesh produced maggots, and dust generated fleas. This simplistic idea had been largely debunked by French chemist Louis Pasteur and Irish physicist John Tyndall in the mid-1800s, although you might better know these guys as the pioneers of milk pasteurization. In particular, Louis Pasteur demonstrated that food spoilage resulted from the introduction of separate microorganisms rather than the magical appearance of life within the material itself. The question, though, is this. Does the Miller-Urey experiment prove that life on Earth began from an inorganic soup repeatedly struck by lightning and bombarded with UV sunlight? Well, the experiment demonstrated that the simplest building blocks of nature can come together under the right conditions. The process by which life started on Earth is exponentially more complicated than that. Moreover, the experiment itself hardly represents the conditions on Earth billions of years ago. Urey and Miller believed that their chosen mixture of gas and water accurately reflected the early Earth, but we now know that this was almost certainly not the case. As such, the ingredients in the experiment should be viewed as a perfect case scenario, considering the unlikelihood that those specific atoms would have been available. More to the point, the idea that the right ingredients would be present when needed and in the proper combinations is highly debatable. To put it plainly, The deeper you delve into the subject, the more you'll realize that having the correct ingredients on Earth isn't just coincidental, it is one of the most enduring scientific puzzles. The scenario is so unlikely that Earth seems to have hit an impossible cosmic jackpot, and remarkably, this may have happened on multiple occasions. What are the ingredients of life? Okay, so to begin, let's clarify the essential ingredients for life in the most basic sense. We need an energy source, the aforementioned building blocks, and water. Regarding energy, there is a virtually unlimited source available, the sun, which sits at the center of our solar system. You're likely aware that Earth is positioned at just the right distance from the sun in what's known as the Goldilocks zone, where conditions are neither too hot nor too cold. This precise temperature range is beneficial for life. However, it can also present significant challenges, as we will discuss a little bit later on. So in regards to the primary building blocks necessary for creating life as it exists on Earth, we require carbon, hydrogen, oxygen, nitrogen, and phosphorus, collectively known as CHNOPS. These are the essential elements for life. To avoid confusion, let's clarify that Urey and Miller used methane, a molecule composed of 1 carbon atom and 4 hydrogen atoms, ammonia, consisting of 1 nitrogen atom and 3 hydrogen atoms, and water, which of course contains 2 hydrogen, 1 oxygen. With these ingredients, we have the tools to create living organisms, achieving varying levels of complexity based on how we assemble these building blocks and how far up the evolutionary ladder we progress. And as a side note here, carbon forms the backbone of all of Earth's living structures, which is why life on this planet is referred to as carbon-based. So, what exactly makes the existence of life on Earth so confusing and so controversial? Well, first and foremost, although Earth is in the Goldilocks zone, it is too close to the sun for carbon and nitrogen to naturally remain on its surface. These elements require colder temperatures to bond and transition from a gas into a solid, allowing them to persist on the planet's surface and become available for making into life. In the colder outer regions of the solar system, solid carbon and nitrogen are much more abundant. However, the scientific community at large maintains that early Earth would have boiled away any carbon and nitrogen real quickly. Carbon's also far more likely to bond with iron than with rock, which means that any carbon present would likely have migrated into the planet's core rather than staying near the surface. A good comparison is gold, which also tends to bond with metals rather than rock. This characteristic is why gold generally has to be mined from the Earth instead of being easily picked up on the surface. Hence, right from the start, we encounter unsolved mysteries that call into question how the required primordial soup could ever have been present on Earth. More to the point, how did liquid water end up on our planet, arguably the most important ingredient of all? H2O is infinitely more likely to bond into a solid, otherwise known as ice, and in most circumstances it will resist forming a liquid state. Moreover, ice naturally tends to form at a much greater distance from the sun, raising the question of how water not only made its way to Earth, but also happened to be conveniently present in liquid form. So, with the mysteries sufficiently set up, let's start exploring some of the proposed answers, beginning with the most supported one. Now, this theory suggests that these unlikely ingredients, including water, arrived on Earth via an external source, in other words, an extraterrestrial shuttle. No, not the big-headed, big-eyed kind that apparently have an uncomfortable obsession with humanity, but rather the chunks of metal, rock, and ice that traverse space. There happens to be an abundant source of these shuttles nearby, and rather ironically, when not responsible for the mass extinction of the dinosaurs, they likely acted as the catalysts that made life on Earth possible. The extraterrestrial delivery system. While the primordial soup theory isn't being dismissed and remains very much a part of the equation, it now seems highly likely that essential ingredients were delivered to Earth via meteor bombardment. It is widely accepted that asteroids impacted our planet far more frequently in the earliest eras of the solar system, particularly during the period known as the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago. This period occurred after the formation of the planets during the Near-Hadean and Eoarchean eras of planet Earth. It is believed that during this time, our solar system's giants, Neptune, Uranus, Saturn, Jupiter, were undergoing a migratory gravitational process, which in turn destabilized asteroid belts and sent them on collision courses with nearby planets. If you're wondering where the proof is, well, look no further than the pockmarked surface of our moon, with many of these impact craters dating to that destructive period. Similar evidence exists on Earth, though it's far more difficult to analyze given the constantly shifting nature of our planet's surface, which makes identifying craters a much bigger challenge. As to whether life on Earth could feasibly have been seeded in this manner? The good news is that the evidence is overwhelming. Numerous discoveries of essential life ingredients have been found in meteorites, with some of the more recent findings being proverbial smoking guns. The Murchison meteor, which fell as a shower in fragments over Australia in 1969, provides a striking example. The fall was witnessed firsthand, and roughly 80 kilograms of the 100 kilogram total was recovered soon after it touched down. The entire meteorite is estimated to be about 4.5 billion years old, making it slightly older than the late heavy bombardment event and even predating the formation of our solar system. In other words, this carbonaceous crondite is almost certainly representative of what would have been impacting Earth during the late heavy bombardment period. Regarding its contents, analysis of the meteorite revealed an absolute treasure trove of scientific information. It contains nanodiamonds, silicon carbides, and remarkably, despite the meteorite's age and the fragmentation it suffered upon entering the atmosphere, over 70 different kinds of amino acids. These are the same amino acids needed to form proteins, which in turn would have been essential for kickstarting life on Earth. The Murchison meteorite alone suggests that ingredients were seeded on Earth rather than forming naturally on its surface. Additional evidence supports this theory. In 2001, a team of researchers from Argonne National Laboratory at the University of California, Berkeley, and Lawrence Berkeley National Laboratory published a paper focusing on whether a comet containing amino acids could enter Earth's atmosphere, withstand the incredible heat, impact the surface, and allow these amino acids to survive. To clarify any confusion, a comet orbits the Sun, while an asteroid travels through space and becomes a meteor upon entering our atmosphere. In either case, the paper concluded that, quote, comets are likewise capable of seeding life on planets. Further support was added by a 2019 French-Italian research team that detected signs of extraterrestrial organic material preserved in volcanic sediment. This sediment, located at Jofstar Chert in the Makonjawa Mountains of South Africa, was estimated to be around 3.3 billion years old. Although it remains uncertain whether the organic material arrived via meteor, its composition was remarkably similar to that found in carbonaceous chrondites, such as the Murchison meteorite. The most logical explanation is that the material was delivered in a similar way, perhaps by micrometeorites much smaller than the Murchison meteorite. An important aspect of this discovery is its location. The Makonjawa Mountains are part of the Barberton Greenstone Belt, which is also home to some of the oldest evidence of life on Earth, including fossilized microorganisms. Whether this alignment is coincidence, that's still up for debate, but the puzzle pieces do just seem to fit together. And the final piece of evidence we can point to is also the most recent. It's from 2022, and it comes courtesy of the absolutely incredible Hayabusa 2 mission, part of a groundbreaking initiative that frankly just doesn't get enough attention. Launched in 2014, the Japanese Hayabusa 2 probe successfully rendezvoused with the near-Earth Ryugu Carbaceous asteroid, approximately 63 million kilometers from Earth. Hayabusa 2 arrived at the asteroid in 2018, carried out detailed mapping, performed multiple landings, during which 2 rovers, Mascot and Minerva 2, were deployed, and even created an artificial crater from which samples were collected. The samples were returned to Earth on December 6, 2020 in Australia, and Hayabusa 2 then embarked on extended missions to visit additional asteroids. Although the analysis of these samples is still ongoing, over 20 amino acids have been identified as of 2022. There was also some confusion when microbial life was discovered on the samples. However, these life forms were definitively confirmed to have come from Earth, having found their way onto the samples via contamination. With all of this being said, delivery via extraterrestrial bodies remains the most supported explanation for the origin of life on Earth. However, there is one other theory regarding the origin of life that is worth mentioning, and it's a particularly compelling one. This final theory is backed by an abundance of evidence, and if it turns out to be accurate, then the likelihood of discovering life on other planets, perhaps even within our own solar system, becomes dramatically more plausible. The oceanic vents theory. The third theory focuses on a more recently discovered phenomenon occurring around Earth's volcanic vents deep beneath the ocean's surface. This discovery also sparked significant interest in the space exploration community toward Jupiter's moon Europa and Saturn's moons Enceladus and Titan, all of which are now considered prime candidates in the search for extraterrestrial life. It all comes down to the identification of microbial life thriving in Earth conditions where it was previously thought impossible for life to thrive. These were a set of hydrothermal vents discovered near the Galapagos Rift in 1977. When scientists explored these vents, they were astonished to confirm that life flourished there. Tube worms, clams, and microorganisms all thrived despite the complete absence of sunlight. Until then, it was widely believed that life on Earth was impossible without energy from the sun, even if that energy only played an indirect role for certain organisms. To put it more plainly, photosynthesis is the backbone of life on Earth, including when a predator eats a plant-grazing herbivore. The discovery in 1977 confirmed that chemosynthesis is a reality, an alternative process to photosynthesis that allows organisms to obtain energy by processing chemicals instead of relying on sunlight. In this case, energy is derived from chemicals produced by oceanic vents. It turns out that there is an entire deep-sea ecosystem that uses chemosynthesis as its backbone, and this landmark discovery opens up incredible possibilities for life on Earth and on other planets alike. In more detail, the study revealed that the life forms around these vents have adapted to utilize methane and hydrocarbons, which in turn offers an intriguing third alternative to the primordial soup and meteor impact theories. A new scenario suggests that the necessary ingredients for life were perhaps provided by chemical reactions occurring on the ocean floor, indicating that life on Earth may have started without the presence of the sun. In that same vein, the moons of Europa, Enceladus, and Titan might have developed life in similar ways. Notably, Enceladus has been observed to exhibit vapor plumes at the South Pole, a strong indication of the existence of similar hydrothermal vents. So at this point, it's time to ground ourselves and bring everything back into perspective. First, let's acknowledge that among the three origin of life theories that we've examined, the volcanic vents version enjoys the least support. Most agree that there are simply too many complications for the scenario to be feasible. It's widely accepted that the sun did play a key role in kickstarting life. The general consensus is that any life forms flourishing near volcanic vents, microbial or otherwise, adapted to these harsh conditions only after an initial origin of life event took place. So now let's turn to Nobel Prize-winning chemist Jack Szostak at the University of Chicago. Szostak dismisses the notion that life began near volcanic vents outright. As the head of the Interdisciplinary Origins of Life initiative, he is a highly respected voice in unraveling these enduring mysteries. In his opinion, it's almost certain that life started on the planet's surface. Quote, "If you look at the chemistry that takes you from simple starting materials up to nucleotides and RNA, there are multiple steps in there that require UV radiation from the sun to drive the reactions. Energy from the sun is by far the biggest source of energy, even on the early planet. So if there are multiple chemical steps that require UV, you can't be in the deep ocean." While Szostak dismisses the idea that life began in the deep ocean, he does confirm that liquid water was a key component. He suggests, however, that life most likely emerged in shallow ponds. Quoting him, "You need a solvent for the chemical reactions to take place. You need a liquid. And when you start talking about liquids, only a few are stable under planetary surface conditions, and even in the early solar system, water happens to be the most abundant. Far more likely than life starting in the deep ocean is that it became established on the surface, probably in shallow ponds or in a hot springs type of environment, the kind of environment that's very common around impact sites or volcanic regions." End quote. And we can now take note of the scalding hot, highly acidic springs that exist today in Norway, Yellowstone Park, and Iceland. In these unlikely conditions, microorganisms thrive despite evidence to the contrary, once again demonstrating how stubborn life can be once it establishes a foothold. The vents in Norway in particular offer key evidence of the Earth's ancient conditions, specifically during the period known as the Paleocene-Eocene thermal maximum, a time when Earth experienced dramatic climatic changes due to an enormous increase in atmospheric CO2. Regarding Szostak's perspective, the most likely candidate for life's origin on Earth is a theory we've already discussed, that the essential building blocks were delivered by extraterrestrial bodies. Even so, Szostak elaborates that it likely was not a straightforward process that could be reduced to a single, easily identifiable scenario, but rather that the origin of life was chaotic, messy, and cannot be easily pinpointed. He adds that poring over minute details and attempting to neatly catalogue the process is futile, arguing that life on Earth was, above all else, nothing more than an incredibly lucky roll of the dice. He concludes that it's best to assume life started through a combination of all of the above theories, and that the process may have even begun on several occasions, potentially by different means over millions of years, only to fizzle out before gaining traction and then restarting under different circumstances. He even suggests that the original microbial organisms, which acted as the true catalysts for Earth's life, might be completely lost to time, leaving behind no trace and remaining an enduring mystery. To illustrate how convoluted the creation of living organisms is, Szostak says, "Life is such a complicated system that the simplest bacteria or virus has thousands of moving parts. It's hard to understand how something like that could just appear out of nowhere? And the answer is that it didn't. It happened step by step, end quote. At this point, in an elaboration of Sostak's words, we can add a little extra context to clarify the equation, a point you might have already considered. Now earlier, we mentioned that meteors likely played a role in seeding life, while also having been responsible for the extinction of the dinosaurs. The dual role is not to be taken lightly, as it is genuinely difficult to comprehend just how destructive and chaotic the late heavy bombardment period truly was. Each of the countless meteor impacts was as likely to completely sterilize life on the planet as it was to seed it, painting a clear picture of just how messy the birth of life on Earth really was. Microorganisms may have been seeded and sterilized countless times before eventually managing to take root and evolve into dinosaurs. Only the cosmos wasn't finished yet, and a follow-up mass extinction meteor might have snuffed out life once again, only for the spark to stubbornly endure this time around. Whatever survived weathered millions of years of winter, ultimately undergoing such profound biological transformations that it eventually gave rise to sentient humans. And while there is almost no doubt that a meteor impact of this magnitude will occur again, that scenario, probably for another video. The bottom line regarding our original topic is that we'll likely never fully understand how life started on Earth, at least not in all its finer details. However, one major clue remains alluringly within reach, and it could potentially offer the largest pieces of the puzzle: finding microorganisms on another planet. This is a prospect that's never been closer. The exploration of Mars is in full swing, and hopes remain high that space pioneers will discover signs of early life on the planet, perhaps in fossilized form as has been found on Earth. There is even still hope that living organisms may exist below the Martian surface, with the methane mystery still unfolding to this day. You can check out the details for that ongoing story in our most compelling signs of extraterrestrial life video, while also learning about the leopard spot rock, which is the most promising sign of extraterrestrial life to date. Beyond this, the keys to understanding our origins may lie on Europa, Enceladus, or Titan, although there might be some time before space exploration shifts its focus in that direction. Thank you for watching.